Hey everybody, this is Moballer12 here to help quench that knowledge thirst. For this video, I'll be talking about alpha-halogenation under acidic conditions. I know it's been a while. It's been about, a week and a half, 2 weeks. And you guys already know that I wasn't feeling too good last week, so that's why I didn't upload a new video. So now I'm just getting back on the grind, and hopefully we'll start uploading more videos. So again, I do have a Facebook fan page, link in the description box below. Show your love and support, like the fan page, tell your friends and family about it. Other than that, I think that's pretty much it. Oh, I hope you guys' semesters and quarters are going, depending on what type of system you guys on. I hope your semesters are going well, or your quarters. Hopefully you guys are acing your classes, and I hope these videos I'm uploading are helping with your guys' difficulties, whatever difficulties you guys are having. Hopefully these videos are clearing it up, or they're just extra, supplemental videos that just kind of, confirm some of the things you guys are learning. So again, I wish you guys the best. Other than that, let's get started with this week's topic. Again, it's alpha-halogenation under acidic conditions. Typically, you see these types of reactions working for aldehydes and ketones, and what we do is we treat it, when we're talking about acidic conditions, we treat it with a specific type of halogen. So typically it's Br2, and the H plus represents the acidic conditions, and then we get the halogenated aldehyde or ketone. First off, let's talk about, because this is an introduction to alpha position of carbonyl, so let's talk a little bit about what the alpha position is. So I'm going to go off on a tangent. We're not going to focus on these things yet. Let's see if I can find some space where I could talk about it briefly. Well, I'll do it right here. If you look at, here's an aldehyde, for example, right? The alpha position for an aldehyde or a ketone, whatever it may be, is the carbon adjacent to the carbonyl carbon. So here's your carbonyl carbon. Your alpha position is the carbon adjacent to it. So this is your alpha carbon, and if this is your alpha carbon, the H's hanging off of it would be your alpha H's. So based off the name of the reaction that I'm talking about, alpha halogenation, we are basically going to halogenate the alpha position, which would be here. This is not a alpha hydrogen, because specifically, sorry about that, specifically the alpha hydrogens are the ones that are connected to a alpha carbon. This is not connected to alpha carbon. This is connected to the carbonyl carbon. So again, the alpha carbon is the carbon adjacent to the carbonyl carbon, and the alpha H's are attached to the alpha carbon. Pretty simple. Same thing applies. So in that case, we had 3 alpha H's. In this case, if we look at ketones, right? We have two alpha carbons in this case, because this carbon is adjacent to the carbonyl carbon. We have this carbon that's also adjacent to the carbonyl carbon. So those are little alphas, like little fishes. And in this case, we have 6 alpha H's, 3 on each alpha carbon, when we're talking about this ketone here. So those are your alpha H's, okay? So we're going to halogenate the alpha carbon position in this reaction, okay? So that should have been a nice little quick review about what the alpha position is and alpha carbon, alpha hydrogen looks like, okay? So under acidic conditions, a few things you should keep in mind. Under acidic conditions, only one alpha hydrogen is replaced, and you're going to replace the alpha hydrogen that would result in the most stable eno intermediate. You guys should know what an eno looks like. An eno typically looks like this, where we have a carbon-carbon double bond attached to an OH group. That's your typical eno, that we usually see. It usually has this type of format, some type of format like that throughout the molecule. So that's your eno, and that's going to be one of our intermediates in the course of the reaction, okay? And we'll look at the reaction mechanism to understand what that means. A more simpler statement than this would be that you're going to replace the alpha hydrogen that's attached on the more substituted carbon, or the more substituted alpha carbon. So let's do this example right here, okay? So what I have done now is I have zoomed in on this portion of the board because we're going to focus on this reaction aspect of it, okay? I already have drawn in the alpha carbons and the alpha H's. I didn't put the little alpha signs by the H's because I think it would have been way too crowded, but nonetheless understand that those are alpha H's because they're attached to alpha carbons. Those are also alpha H's there. So in this case, this statement here is extremely important when drawing the product. It says we're going to replace the alpha H that would result in the most stable enol intermediate. Another way of looking at that statement is that we are going to replace the alpha H. Obviously I don't have it written here, but we're going to replace the alpha H that is attached to the most substituted alpha carbon. Now again, these are your alpha carbons here. This alpha carbon is primary. It's a primary alpha carbon. This alpha carbon here is a secondary alpha carbon, right? It has two carbon groups attached to it. So the most substituted alpha carbon is this one here. So we're going to replace the H that's attached to it with the bromine. So our product is going to look like this. Simply put, our product is going to look like this. And that's it. It's as straightforward as that. We have to find the more substituted alpha position, and if there's an H there, we're going to replace that H with the halogen, and that's only under acidic conditions. Now let's take a look at the reaction mechanism, and then we could understand this next this statement here, okay? How that statement works, okay? So the first step in the reaction mechanism of this alpha halogenation under acidic condition is we're going to protonate our system here, okay? So there's many ways of showing the reaction mechanism. Specifically, the way I learned it was this very straightforward, simple, hard and dry, fast reaction mechanism. So we use the pi electrons from this carbonyl to, protonate the system, and we get this intermediate here. We get an alcohol, but effectively we formed a carbocation as well. That's a positive charge. Let me zoom in a little bit on that position. Okay? So again, we protonated our system, and we get this alcohol, and we get this positive charge here. Now here again, we have two options. We could get rid of this H here or this alpha H here. Now in terms of this statement up top, replace alpha H that will result in the most stable enol intermediate, we're actually going to lose this H here to form this enol intermediate here. The reason why is because this enol intermediate is more stable. Okay, how do I know it's more stable? Well, it's more substituted. This alkene that we formed here is more stable because it's more substituted. Now, if I were to select this H here to, so let's just say, for example, we select this H to be lost in the course of the mechanism, the enol we could have formed would have been this guy here. If I would have selected this H here, we would have formed this enol here. And that is not as substituted, that is not as stable as that enol there. We want to form the alkene that we generate from this step. We want it to be most substituted, and that is what results in stability. A more substituted alkene is more stable. So this enol overall is more stable than this enol that we have generated here. So this pathway is wrong. That's why we select the H that will result in the most stable enol intermediate, or we select the H that's attached to the most substituted alpha carbon position. Those are two ways of looking at it. I hope that makes sense. Now that we have generated our enol intermediate, now all we have to do is recreate our ketone. The bond between the oxygen and hydrogen is broken to reform your ketone, and this alkene now is going to the pi electrons from the alkene are going to attack the bromine from the Br2 to generate your halogen at that position, this position here, and that is what we get up there, and we lose this bromine as a result as well. So that's pretty much it in regards to the reaction mechanism. In regards to the reaction itself, very straightforward. All we do is find the more substituted. To make things very simple and not complicated, is we determine where the more stable enol intermediate we could form, or better yet, we identify the more substituted alpha carbon, and if there are H's there present on that more substituted alpha carbon, then we're going to replace it with a Br. As simple as that. So let's just do a few examples. Let's do like one or two examples. I'm gonna erase this stuff here, and we'll call it a day. So 2 examples. Let's just say we have let's try to halogenate this system here. Okay. So first off, let's identify our alpha position. There's our alpha carbon there. There's our alpha carbon there. Okay. Now we have to draw in our alpha H's. So we have one alpha H there, and I see another alpha H there. Okay. Now this position does not have any alpha H's. It already has, this carbon already has 4 bonds to it, so we already have fulfilled the octet. We can't have any other H's there present. So this makes our life extremely simple. All we have to do is replace the H from here, one of the H's here. So our product will look like this. And it's as simple as that. Now again, you might be confused and thinking that, well, isn't that the most substituted position? Shouldn't we try to put the BR there? Of course, that thinking is perfect. That's the way you want to think about it. But how can you put a BR there? Because keep in mind, we are replacing an alpha H for a bromine. How can we replace an alpha H in the first place if we don't even have an alpha H to start off with? So since we don't have any alpha H's in this place, we can't really replace any of them here. And as a result, we have to resort to our next position that would have alpha H's there. So in this case, we would have the BR in the less substituted position because, again, we have no alpha H's to start off with. So that's something to keep in mind. So that's the product for that reaction. Let's do one more, and I think that's what I'll end it off at. So let's just say we have let's just say we have that, and we do again Br2 H plus. Identify our alpha carbons. There's our alpha carbon. The alpha H's would be right there and there. In the case of an aldehyde, we only have one alpha carbon, and as a result, we only have, in this case, we have 2 alpha H's. That is not an alpha H. Okay. So we're going to replace one of these alpha H's. It doesn't matter which one, with the bromine. And we're done. And that's what alpha halogenation is. Okay. Hopefully you guys benefited from this video. Hopefully this video made sense. I really appreciate you guys watching. And until next time, this is Mo Baller 12 signing out.